Azure Service Bus. I'm Matthew Hess. I'm from Albuquerque, New Mexico, and I realized I've never been to Milwaukee. I've traveled so much for work, so many places, and I'm really excited to be here. So thanks for having me. And it's really lovely to see such a great in-person turnout. It's just exciting to see people actually wanting to get together as actual human beings and share physical space and interact to do these things we maybe forgot how to do a little bit. So congratulations and thanks for having me. So a couple acknowledgements before I get started. First off, I always just really have to thank my Uncle Mel. I just have no idea where I'd be in this world. Thank you, Uncle Mel. It meant the world to me. I want to thank my employer, CG Infinity. So it's a Plano-based software consulting shop. It's actually just a fairly enlightened organization and really a great place to work, good people, and they're super supportive of these activities. So thank you, CG Infinity. It's an interesting organization. You can go find it on through my LinkedIn and stuff if you're interested. Good place to work. And thank you guys. Again, this is cool. You've got a really thriving community here. So I think Vancouver beat you all by about 10 people, but you know, it's close. You could start having a contest. You and Medot can have a little, get a thing going and see if you can drive turnout. So just a tiny bit about me. So, you know, I have this funny thing. I call myself the C# artisan, and that's a little weird. What's up with that? Like the C# artisan. So there's this question we ask, right? Software development, is it an art or a science? And, you know, to me, it's neither. Now, don't get me wrong. I know there are real computer scientists. I've known a few of them. I've attempted to socialize and understand what they're talking about. And they do incredible cutting edge research in graph databases and AI and stuff. So computer science is a thing, but that's not me. Okay, and I think all of us, as we write code, we sometimes feel there's an aesthetic side to it, right? It like good code is appealing, and so there is an artistic part to it. But day in, day out, year after year, now decade after decade, what I've gotten paid to do is the equivalent of software bricklaying, like just make stuff that works. Architect, design, put it together, make it robust, reliable, and it's artisanal to me. It's a craft. So I don't really view myself as any different as any of you all. I don't have some special access to, you know, Anders Salzberg or other inventors of the C# language, right? We're all out here learning, trying to keep up with the times and the tech, trying to get better at our craft. So I do these things. It's a bit of an educational mission, which is like, let's all just level up. It's easy to write crappy code. It's easy to write middling code with the help of an AI chatbot. But to write good code still does take some HI, right, human intelligence, and a little practice. So that's my goal, is just help us all kind of level up. And if you walk away from today's talk and you've learned one or two things, and you're just like, oh, I never thought of it that way, or that's cool. Success, right? At that point, we've done our job. So that's why I'm in it. That's what I get out of this. If you would like to interact with me, if you at the end of this, if you're not just completely sick of me, you can connect on LinkedIn, right? And so hopefully everything you need is on this one thing if you want to take a picture of it. I have this YouTube channel. Would be delighted if some of you would take the time to go look. Maybe subscribe, like a few videos. Kind of a mishmash of interesting content, you know, but hopefully that's good. And I'm always looking for suggestions. So if there's something you'd like to see, I'd like to hear that. You can email me. I occasionally check that one. Today's talk actually has a code demo at the end, and the code is there if you want to go get it off of Git. Okay. So you all ready? Let's get on the bus. So what is Azure Service Bus? So now we get this great text-heavy slide. Azure Service Bus is Microsoft's cloud offering for developing message-based applications. So what on earth is a message-based application, and why would you want one? So let's take a little time at just understanding why would we even do this of the conversation. But first I want to say, like, it's called Azure Service Bus, and that word bus has always tripped me up a little bit. Like, bus? What are we talking about? What kind of bus? And if you've done electronics or torn into your computer or anything, you know what a bus is in electronics. It's a hardwired, high performance, point-to-point data shuttle, right? It gets the information off your CPU into your RAM and other things. And that is not what messaging-based architectures do. They're not high performance. They're not hard-coded. So I do not know why these things are called buses. I just wish they had called it Azure Service Queue or Azure Message Queue or AQ, Azure Queues. Because has anyone done Microsoft Message Queue? Anyone old enough to have done MSMQ? Right? This is cloud-hosted MSMQ with a lot of other features. When you get inside Azure Service Bus, what you see are queues and topics, which are Microsoft's way of kind of dressing up queues. So this is queues and messages. So if the term bus makes you feel, I don't know, excited in some way, great. But I just like to think of it as Azure queues. Okay, so why a message-based architecture? So let's get into the real world. Let's just imagine that you didn't just have a bunch of pizza and you're feeling a little hungry. You'd like a snack. Okay, you're like, I know. You walk out the door because there's a vending machine down the hall, and you put in some money or you scan your card, you make a selection, and your Munchie Crunchos, fall out the bottom, and then you get to satisfy your desire for a snack. So that is like a synchronous or tightly coupled interaction. You put a command into the vending machine and you got a response. And if this is a tech talk, don't worry, we're not just going to look at pictures of food. So here is a small UML sequence diagram modeling that interaction as a sequence. So you're the customer, and you called this command called make selection, and the vending machine returned a result. It gave you your snack, or maybe it gave you a 404 snack not found error or something like that. But you got a response back. You didn't wait around, right? You there, and it came out. That's tightly coupled or synchronous. And that's a lot of what programming is, right? I mean, tons of programming. You call one C# function, calls another C# function, and it returns, right? A REST API, you call your REST API, and you get a result. That's how we write code. So what's the alternative? So now let's say that the Munchie Crunchos just didn't really cut it, and you're really hungry, and I've teleported you to Albuquerque. And so what you would then do is you would drive down Central Avenue and you would go to Duran's Central Pharmacy, and you'd walk in and you would order an amazing New Mexican meal at the counter, and you would have a great time. So you would place your order. It would get sent to the kitchen, and then somebody would bring it out to you. Okay, Duran's is amazing. If anyone ever gets to come to Albuquerque, look me up. I'll take you to Duran's. You might have to. You're from Wisconsin. You might have to train a little with some chilies. Like habituate yourself. Come on in. Come on in. So, okay. So what's that UML sequence diagram look like? Complicated. So you're the customer, you walk up to the counter and you place an order. And then the magic thing happens. Your order is in queue. So the key fact here is that order queue. That's the key thing. And so in the restaurant, in Duran's, it's actually an old-fashioned little metal spinny wheel that tickets get put up on. That's the order queue, right? And then somebody in the kitchen dequeues your order, cooks it, and then it gets sent out. Now there's actually a second queue, the runner queue, where they ding a bell which says there's an order ready, but that makes the diagram too complicated. Okay, so that's how a restaurant works. A restaurant is a message-based system, most of them. It's a queue-based system in the room. So what is the benefit of this? Why do restaurants work this way? Why doesn't the person who takes your order go back and cook it for you and then bring it right out? Right? It's because you want to implement the counter separately from the kitchen. The counter has different requirements completely, different training, different people, different tools, and very importantly, different scale needs, right? On a busy Sunday brunch, they might have to put 3 people on the counter, but 10 people in the back cooking, right? They scale differently. So those systems want to be implemented separately. They have their own logic, right? They are, I don't know, microservices is a buzzword, but they are services. I don't know how micro they are. They are separate services and they need to communicate. So that's the rationale, is to decouple pieces of a complex system. And the reason you want to decouple things is because they have different needs, different architectures, different languages, different scale requirements. So that's the real world understanding of why you would do this. Now, I'm not sure if there's, yeah. So right before we wrap up, this is what you got. These are the green, the blue corn enchiladas, and we would order at Christmas, which means give me red and green chili. It's really delicious. Now that I made you super high, it's a good thing you brought some pizza, I guess, right? Yeah. And so in the real world of software, you can think of all kinds of systems that behave this way. Imagine you log on to Amazon and you place an order, right? There's a system that records or that updates your what is the thing, or the shopping cart, right? And then places the order, but then there's pick, pack, ship, and the email notification, and billing, and like there's all these systems, and they are not tightly coupled. They talk to each other through messaging. So when you play buy, something says to the pick, pack, ship service, okay, here's something to deal with. It's all decoupled. So that's why we do this. So we've convinced ourselves that this is something we want to do. If you now think like, oh, I'm never going to do that, you can. Okay, so that's the why of it. Now, before we actually write some C# code, you're going to have, so we're using Azure Service Bus, right? We're not doing this in Kafka or RabbitMQ or some other similar or adjacent technology. So you're going to need some Azure stuff set up. So here are your technical prerequisites. So in Azure, when you're doing, you can go on the portal and do this with clicks, or you can write some CLI, Azure CLI. But the first thing is you have to create a service bus namespace. So a namespace is a container, and all it really does is let you create queues and topics inside of it, and it creates sort of a way that you can organize stuff, and it exists in a resource group, which is your billing unit. So you can do the CLI, AZ Azure Service Bus namespace create, and you say the resource group, you give it a name, and you give it a location. And then once it's there, if you go on the Azure portal, you'll see your namespace created. That's step one. You got a namespace. Next, you need to create your first queue. Again, here's some simple CLI to do that. You say the resource group, you say the namespace, and you name your queue. And once your queue has been created, you can look at it and you'll see, oh, I've got no messages, no active messages, no dead letter messages, no scheduled messages. I've got a queue ready to use, and it has a name. Now, all the C# code points to a library, right? A NuGet package, which is the Azure.messaging.servicebus namespace, which is in Azure.messaging.servicebus package. So however you like to install your packages, you can do it that way. And then this isn't like a prerequisite. It's just something that happens every single time you interact with Azure Service Bus. It's the code that is the equivalent in some ways of SQL Server making a connection, opening a connection, right? It's the thing you got to do first before you can kind of work with your queues or your messages. So This is called you're creating a service bus client. And again, it's similar to you can kind of think of it as like a SQL Server connection. So to do this, there's a couple ways to do this, but a very simple way. So first of all, you do need the namespace, and it is this fully qualified namespace. So you called it test bus namespace, but you have to tack on .servicebus.windows.com. And then in production, you would probably have some sophisticated, authentication scheme, right? Where apps, users, services can authenticate in different ways. And the default Azure credentials construct kind of supports that cascade. Like it'll try a sequence of different things and let you authenticate in different ways. So in production, this is probably what you would see, but this is not a class on Azure, on Entra ID and Azure authentication, and I'm not the guy to teach that anyway. So this is just an example. And then when you are about to create it, you have some options. So I've chosen the high performance AMPQ WebSockets way of doing this. And then I simply instantiate a client, passing in the namespace, the credentials, and the options. So now I've got a client, and I can do all kinds of stuff. For the test project and for development, there's a way you can do this where you just use a connection string instead of this default Azure credentials and having to set up a lot of complex stuff. So a connection string is this long, horrible string, and that you can get it through the Azure portal. You go to your namespace, and I can't remember off the top of my head what the clicks are, but basically you can retrieve the connection string out of the Azure portal in your namespace, and then just put it in like an app config or wherever you're storing your secrets for your test project. So in the Git, when you download the code, there is literally an app.config and a place where you can paste in your connection string. There's a CLI command to enumerate all of the strings if you want to just fish them all out from the command line. So once you have a connection string, oops, what just happened? I want to go back. I think I missed saying something. Nope. Okay, well that fell apart pretty fast. What I meant to show, well, okay, it's on this slide. So then to instantiate my client, instead of passing in the credentials and all this jazz, I can just pass in a connection string and get a client. Okay, so now let's send our first message, right? This is messaging. We've established the queue. So now we're going to want to send a message in, receive a message out. Those are your foundational kind of concepts, right? It's going to start moving a little faster and getting complex, but let's make sure we have, our feet on the ground first. So I create my service bus client. I somehow decide which queue I'm going to address. I create a message, and there is a constructor that lets you just put in the message body right there as a string, and I send it. Now these are all async, right? There's all send message async. I have a whole series of video tutorials and a live talk on async await, because async, this is an aside here. Async await is something that I thought I understood and actually did not at all understand what it really does. We all use it. So if you are like, that's interesting, there's some stuff you can find on my channel that might open at least some questions and hopefully some answers about what all this async jazz actually is. It surprised me. So, but we await it because it's async. Okay, so now once we've sent a message, you can see we have a message in our queue. So that's your basic message send. So far, so good? Yep. Now, let's receive that message back out. So again, we create a client, we decide which queue we want, and now we create a service bus receiver. So we had a service bus sender. Now we have a service bus receiver, and all these classes are given to us. Okay? And then we have what we get out. Notice we created a service bus message, but what we get back out is a service bus received message. So technically, they're actually different classes, though they share a ton of properties. So that's what you get. And when you receive a message, you're not always guaranteed to get something, right? You're awaiting that. If there's no message in the queue, you're not going to get a message. So check. If we actually got a message, then complete it. Now, that is weird. This is the first thing where you're like, wait, what? What is that? I'm going to spend a bunch of time talking about that. So just for now, this is to make this so it will compile and do the right thing. That's the way it needs to look. And you can see on the portal, I took a screenshot of the two messages, one being sent, and then a little bit later, one being received. So we sent a message, we received a message. Okay, so now we're going to unpack this a little, get a little philosophical about a few things, and then we're going to dive into practically how some of the real meaty stuff about building message-based apps that actually work. Because sending a single message and receiving a single message is not probably what your clients need. But first, I just want to mention, again, a little queue theory. So queues are a first in, first out data structure, a FIFO data structure. So what that means is if your sender sends 3 messages, M1, M2, and M3, and then your receiver starts receiving them, they're going to come out M1, M2, M3. First in, first out. That's important, right? That's how queues behave. That's how we expect them to behave. And unless you jigger around, Azure Service Bus will enforce strict FIFO ordering. You can subvert it, but it'll give that to you if you're careful. Now, there is the concept in Azure Service Bus of topics and subscriptions. And if you've done Kafka, you're like, oh, I know what that is. And this is not the same. It is not this sophisticated pub/sub, highly flexible architecture. It is actually, as far as I can tell, simply a way to create and send messages to multiple queues at the same time. When you create a topic, okay, a topic is like the input side. But notice when you look on the portal, when you create your topic, it doesn't have a message count, right? Topics don't store messages. They're just kind of this gateway. And then you end up subscribing. And every time you subscribe, that sort of creates the queue. So what happens is when you send a message to a topic, what it appears to do is actually put a copy of the message in each queue. Now, in terms of the implementation, I don't know what Microsoft is doing on the back end. Are there actual pointers to a common thing? I don't know. But functionally, what happens is you send it to the topic, and it puts a clone of that message in each subscription. And then, so the pattern for receiving is like this. All right, I sent that M1 to the topic, and all 3 subscribers got it. I sent M2 and all 3 subscribers got it. And then my subscription 1 subscriber received it out, right? And now M1 is still in the other queues, but it's been received from there. And if you look at the subscription, it looks just like a queue with message count, active messages. Okay, so it is pub/sub in a way, but it's not super sophisticated pub/sub. But just this is nice. It lets you do. This is a convenience. Okay, you should be aware of. For the rest of the talk, I'm just going to focus on simple queues, just to keep our heads screwed on straight. Okay, so we've decided why we want to do this. We understand basic mechanics of send and receive, how that's going to work. But what are in these messages? Like, what are we actually sending? So I want to spend a little time talking about message payload. What are you going to put in your messages? So I make a distinction between what I call heavy messages and light messages. Now, this is a Matthew term. You're not going to go find some O'Reilly book where someone else talks about this. But I have heard people talked about like stateless versus stateful messages or other ways of describing this distinction. But it's basically like a heavy message has a lot of stuff in it and a light message doesn't. So to describe this, let's imagine that you work you put together sales proposals. You work for some sales organization, right? And you put together proposals and you try to sell stuff. And now let's go back 30 years. So how would that have worked? Well, you might have opened up Microsoft Word or WordPerfect, and you would have typed out your thing and printed it out. And then you would have printed it, stapled it, and put a sticky note on it that says, please review, and you put it in your reviewer's box because your company has a strict no proposals without review policy. Okay, so you compose it, you submit it, boom, physically in the inbox. And then eventually that inbox is that person's queue, right? And they will fish it out and read it and review it and take care of it. So that was the message. The full printout of the proposal with the sticky note on top, that is a message. Hey, boss, review this, please, right? And it's a heavy message because it contains everything the reviewer needs. They don't have to like go log onto system and retrieve it or go walk down and pull it out of a file cabinet. It's there. It's complete. It's self-contained. So that's kind of the hallmark of what I think of as heavy messages, is they are stateful. They contain everything you need to take action. Okay, so that's one style of sending messages, and they contain a lot of data. The other, right, so now let's say this is implemented in a modern CRM and Salesforce or whatever. Well, it's a different process, right? As you author the proposal, it's saving it into whatever the backing persistence database is. And then when you're ready, you're like, okay, I think this one's good to go. You press submit. And what happens is a message pops up in the reviewer's, Slack or Chatter or whatever, messaging system they're using. And they're like, oh, great, Matthew sent me another one. And they receive it. And then when they open up the window to review it, it actually is going to, at that point, retrieve it. So out of the database. So the message itself is very light. It's like, you have something to review. Here's the ID. Maybe just a couple of fields, an ID, a date, who submitted it, the client, maybe the total dollar amount or something, right? It's actually like they just got the sticky note. Like you peeled the sticky note off of the proposal and gave them just that. So those are light messages. And this is more of an event-like way of thinking about this, right? An event happened, right? Something happened in the world. And now you get to look at the event, the summary of the event, and decide, do I want to take action? And if I do, then I probably have to retrieve stuff and take action. So the distinction, I'll look at payload in a second, but the choice between these, it's important that you're intentional. You choose which, and there are pros and cons and some trade-offs that you can analyze. But I just point this out because you want to make a choice. Like, what kind of architecture am I doing here? And the advantage of the event-based way of doing it, the light way, is that it's lightweight, right? In events, and then your clients can decide, or the receiver can decide, do I care, right? You're not passing a lot of data around. It's natural. However, it does sort of entangle the sender and the receiver because they both then need access to the common repository. Whereas if you just sent everything in the message, then they are truly decoupled completely. Like, here's all the data, do with it what you want. But then it creates some message ordering issues of like, what if there's a revision that comes later and you read them out of order? So I'm not going to go much further than that, but it's important to acknowledge the difference, think about it, and make a choice. So how would you do this? Well, Azure Service Bus makes this super easy. So generally, we can model our messages as little data classes. People call these POCO classes or serialization classes or data classes, right? Okay, we've got a bid ID, bid date, customer description, and amount. And then you can simply serialize it with a little JSON serialization, and then you can send it, right? So I'm creating a Service Bus message equals new message, and the body equals the bid. Okay, so the body is actually binary content. So this works really well when you do it this way. Oh, sorry, I messed that up. Let me do that. This is an OR. So One way you could do it is call that constructor that takes a string and use serialize it. Sorry. And then the other way is you can use the empty constructor and then set the property in your property initializer clause there. And the service bus framework, if you pass it an object, will automatically apply based on serialization to it for you. That's what I meant to say. Sorry. Did everyone catch that? I had to rewind and redo that.
So ultimately your body's always a string.
Binary content, not a string. This constructor just does the magic for you. Okay. So now this works for both heavy and light pattern, right? If it's light, this only has a few fields. If it's heavy, this JSON document could be massive, right? And have subdoc, right? Whatever you want to serialize, you can jam on in there. That's fine. So that works for both. But there is also a way to actually model that whole thing of like the document and the post-it note quite explicitly, where the subject is just your little string serialization of that header. And the body is actually maybe bytes. Like, so this is a byte array that I read off of the file system in this case. And so I can just put binary data in the body if I want. By the way, this syntax here, using the target type new constructor and the initializers, this is somewhat new C# syntax. And if you learned C# 2.0 like I did, you're like, this might look a little different to you. And I have some videos on like newer C# features that are really cool that maybe we all should be moving towards. And the target type constructors where the constructor figures out which one. So this gets rid of var. Okay, this is my don't use var anymore speech because you don't have to. Instead of saying var message equals new service bus message, you can write normal looking C# where your variables have types. Thanks for coming to my little mini TED talk within the talk there. I love this style. This is more modern. And AI chatbots, GitHub Copilot will not necessarily suggest this style because there's so many code examples written in pre-C# 7 and C# 8 where some of these things became available. So, okay, so that's the main talk about your body. One last thing about correlation IDs. So when you decompose or build a complex system with multiple services that are wired together with these message hops, one of the real challenges of this can be tracing the journey of a single kind of event, right? I placed my order on Amazon. I got an email confirmation. It went into pick, pack, it went to ship. I got a ship notification through the email server. There are all these things, and then I didn't get my package. And what happened, right? So tracing the journey of that thing through that is a bit of a problem because each of those services or microservices has its own logic, its own logging, its own persistence. So the concept of a correlation ID is that at the very beginning, you stamp the thing with an ID that's going to follow it all the way through, like the existential event of like ordering my socks, right? As it gets handed along, it gets an ID. And this is such an important microservices concept that it is a first-class property of the message object. That's how important this is. They carved out a space for it. Didn't make you just put it as the first property of your body or embedded in the subject. So I strongly, strongly, strongly encourage you to do this. And the pattern is the thing that kicks off the very first message in the chain. I use GUIDs, right? Almost always just make a GUID, serialize it, and stick it in there. And then it's the job of every subsequent hop to pull that off its message and put it on any subsequent messages. And then if you use, for example, like one I recently used, a log drain called Datadog, where all the different systems can huck their stuff into Datadog. Datadog doesn't care. But then you can use the simple wildcard search on the correlation ID and get the journey across the whole microservices thing. And then there are other tools that that understand correlation IDs and can do this for you as well. But it's a really, really important concept. So again, if you walk out of here and you haven't learned anything, but you was like, oh, maybe I should think about using correlation IDs, I think you learned something valuable. All right. So yeah, we might run a tiny bit over. I'm moving a little slow. Probably have
Those timings guidelines.
Okay.
Necessarily hard to stop.
I'm trying to learn to talk a little slower because I've realized that sometimes I start sprinting and mumbling. And that sprint and mumble is a technique that works for certain stand-up comedy things, but isn't so good for tech talks. Okay, so those are the fundamentals. Why are we doing this? Kind of send and receive. What are we putting in our body, in the message bodies? So now we need to look at some of the, like at the beginning, I said, it's kind of like MSMQ with some cool options. So let's now dig into these receiver modes and options and some of the bells and whistles you have in the real world. So the first thing is receive timeout. So you remember in the code, my first code, I said receiver dot receive messages async. And I said, and it might not get a message back to you, but you're awaiting it. And so how long are you awaiting it? So the default is a minute. If you don't specify, that code is going to sit there awaiting. It's going to sit on the continuation for a minute, and then it'll pop back to life and tell you you didn't get a message. So if you want to control that behavior, you can specify that when you call receive message async, you can specify a timeout with a timestamp. So in this case, it'll come back after 5 seconds. And then check if your message is null process. So that's your first important option, is receive timeout. The second one is the receiver mode. And this is the most complicated concept out of this whole talk. So we need to stretch. It's getting a little warm in here. You guys okay? I lulled you to sleep, and now I'm going to hit you with the hard stuff. So there are 2 receiver modes, peak lock and receive and delete. Peak lock is the default, and it's more complicated. Receive and delete is very simple, but it's not the default. So I'm going to show you receive and delete because it's the simplest, and then we'll spend a little time with peak locks. So if you want to use receive and delete, because it's not the default, you have to say, okay, I'm actually setting my receiver mode, my receiver options explicitly, and I want my receive mode to be receive and delete. Then when you create your receiver, you pass in the options. So that's how you're controlling its behavior. And then you can receive your messages, okay, the same way you did once you've made your receiving. So that's an option at the receiver message or receiver level. So receive and delete does just what you think, right? Somebody put a message in the queue. When I receive it, it's gone from the queue immediately, right? You make that one request to the cloud, give me my message. And then if anybody else looks in the queue, your message is gone. So receiving equals removing it from the queue. So that's very simple and natural. That's how FIFO should work. And if it was all just not on the cloud, right, that's how MSMQ did work by default. If you wanted to do other things, you'd have to peek ahead. So it's simple, but it does place a responsibility on the receiver to make sure you don't lose it, because there's no other copy of it. You have no recourse. You have no retry. You received it, it's yours. It's your baby. You better handle it. So it's a very simple pattern, and it's great for a lot of applications. Just think about fault tolerance and making sure, like, what if my code crashes? What happens to that message? The default is peak locks. This is a little complicated. So I'll do a little modern dance and dramatize what actually happens with this. When you are using peak locks and you receive a message, so receiver dot receive message async, you get the message, but on the server side, up in the cloud, the message gets marked and locked. It says, okay, that one is locked. Right? It's been received, sort of. And a timer starts. Stopwatch starts. If another receiver tries to access that queue and receive messages, it will not get your message. It will get the next one. Now we've broken FIFO, actually. And then the server waits for the client. The message is locked and it waits for you to take some sort of completion action. You have to take a completion action, which is a second message, right? A second command to the server. And the simple one is complete the message. If you say, I complete it, then it's like, great. Then it deletes it out of the queue, right? And so that's the behavior, right? You receive it, you have a certain amount of time to finish the job and tell the server what you want to do. So what are your completion options? The one I just talked about, and the one I showed you in that first early slide. And it basically says, okay, the message is removed from the queue. This is used for normal successful message processing. So that's the normal pattern. Receive, complete, receive, complete, receive, complete. That's what they look like. There are two others you can do. You can dead letter the message. So the message is removed from the queue and placed in the special dead letter queue. Did you notice there were some metrics, right? There was the queue, active queues, active messages, dead letter message. It gets put in the dead letter queue. This is generally used when a message is not processable, okay? Basically, it's like a poison message, right? You're never gonna do anything good with it. It's not gonna get better. It is possible to replay messages out of the dead letter queue using the Azure CLI portal and various tools. So I'm going to talk later about situations that are avoidable where you get lots of good valid messages piled up in the dead letter queue and you need to replay them. But you can avoid that for the most part. But that's what the dead letter queue is for. You can also abandon it. And this is really confusing, because it means abandon from the client perspective. So I use the baby metaphor, right? Like, give me the baby, but I'm abandoning the baby. That means it's your problem, server. I don't want it anymore. Okay, it doesn't mean server abandon it, right? It doesn't mean we're giving up on the message. So what happens when you abandon a message is the lock is removed and the message goes back in the queue. So if you receive again, you will get that same message back. So visualize that, right? There's this message. I received it. The timer starts. And I say, no, thank you. I abandon, and it goes back. And then I receive again. I'm going to get that same message back, right? Because it's FIFO, and it keeps its place in the queue. It doesn't cycle them to the back or something like that. So abandon means, no, I'm not going to process this one right now. There is this option to defer, and defer by the way, sorry, with abandon, I should read my own notes. So the message is unlocked, and there's this thing called the retry counter is incremented. Okay, it was received once and not processed. And then you receive it again and abandon it, and now it's received twice and not processed. So that is incremented. So this is used basically when the message might be able to be processed. It's salvageable. You want to put it back in the queue and retry it later. The number of allowed retries is configurable. So by default, when you've pulled it 10 times, then it dead letters. So you receive it and abandon, receive and abandon, receive and abandon 10 times, and it says you're done, and it puts it in the dead letter queue. So that's configurable. You can say, I want 50 retries or 3 retries. So these two kind of interact in an interesting sort of way, right? So the 11th receive would cause it to abandon or to dead letter. Deferring, the message technically stays in the queue, but it's marked as deferred, and then you have to use, and it's given this like sequence number, and then your other methods called receive deferred message. It just creates this parallel universe of handling deferred messages. I don't use it. I'm like, why? What is that? What problem does that solve, right? If you know and have seen it used, please tell me. I'm eager to hear. But for me, I just am saying should be used with caution because I think it creates, some of this is complex enough. And I think that creates this extra complexity that I haven't found a value for. Okay, so then what about that stopwatch, right? What happens if you don't complete it or dead letter it or defer it or abandon it and you run out of time? Well, that's an abandon. And it's 1 minute by default. So you receive the message and your client process crashes, goes away, right? Well, I don't know why. A minute later, the server is going to be like, well, I guess you're not that interested, and it'll abandon it for you and it'll go back. So as I talk through this, you can maybe start to imagine some of the nightmares, train wrecks that can happen because you get 10 retries and a 1 minute timeout. And like, if something is down, this can become a dead letter machine and a huge amount of compute as it churns through all your stuff doing nothing, right? So we're going to talk about some of these patterns so you can avoid them and not come into work tomorrow morning and see 68,000 messages in the dead letter queue and wonder what the heck happened. Okay. So again, just to review, peak lock expiration is configurable. So I have actually pumped that up to about 5 minutes in certain cases where the thing we were doing in processing the message required talking to a fairly unreliable and slow API. And sometimes things would come back right away, and sometimes they wouldn't. And we knew that if we gave it a little time, it could probably sort itself out. So we lengthened that in order to just create a little elasticity so that it didn't always retry. All right, so receive and delete comes right out. Peak lock, you have a lot to think about, some choices to make.
Question.
Yes.
Are you able to set the timeout per message or no? Or just one of our?
Okay. So the receive timeout, there's 2 timeouts we've talked about. The receive timeout is like my receiver says, are there any messages? How long do I wait? That's, yeah. The second one, the is configured at the queue level. You do it in the portal.
Okay. But not per message. So my instance is we have a queue system right now. We have various reporting that goes through, and some take longer, some doesn't, but they all go through the same queue.
Yeah. Okay. So the first setting there, max delivery count, that's the number of retries before it dead letters. That's the number of abandons you get. And the message lock duration is the one you're talking about. It is configured at the portal, at the queue level, not even at your receiver level. Right? You're not really setting that at runtime. That's a configuration of the queue. That answer your question?
Yeah.
Yeah. Okay. Good question. Thank you. All right. So in the real world, when we build a receiver, it's meant to handle a lot of messages, right? You tailor it to the load and the app. So there are a couple of patterns that I've used when building these receivers. The simple, in some ways, it's the most code, but it's conceptually the simplest is your basic message pump. So a message pump, like the Windows event pump, like the thing that runs our operating systems, is just a loop that checks an incoming queue for messages, right? It's a long running loop. In Windows, it lasts until you put your computer to sleep. And so a message pump is a very simple, well understood construct. And here is a fairly complete, I'll show you what's missing, message pump. So we're starting our message pump here. We're passing in a cancellation token. That's important, right? This is called the cooperative cancellation pattern. And it's how like a server type thing that is kicking off a long running loop, a thread or a pump or process can ask it politely to stop instead of just killing it, right? And I have a video on cooperative cancellation if you're interested. You can implement it yourself or you can use the C# pieces. So that's what that is. It lets us stop the pump gracefully. And then the polling interval, right? So this pump isn't going to churn, right? It's going to pause on each loop between, and we want to configure that. Okay, so we've got our queue name, right? We got our client. We create the receiver, and we've got our timestamp for our polling interval. So that stuff all gets set up. And then while not cancellation token is cancel requested, so this is our long running loop. So basically, until somebody tells me to stop, do this while loop. Try to get a message out, right? Await receiver.receive message async. And here's your timeout. And notice that actually creates a natural polling interval. We don't have to do an await delay or something like that. Because if we said poll every 10 seconds and there were no messages, well, this is just going to sit here for 10 seconds and then try again. So it's a natural way to implement that poll. And then if we got a message, process it, right? This does something, whatever that is, and then complete it. And then the other thing you see here is I'm catching any exception that happens in here. And for now, I'm just saying, okay, we'll just abandon it. And this will cause it to come back in right away. And we'll talk about that. But that's the basic scaffolding for a message pump. So I'll give you guys a second to, does that make sense so far? Okay. You just rolled your own receiver. And then something is turning it on and letting it go. And then eventually turning it off. So another thing that you should have at your disposal is the idea to receive a batch of messages. So instead of receiving a single message, I can get a little packet or array of messages. So really pretty straightforward. Make my client, get my queue, make my receiver, get my time span, and then I've just said, what's my batch size? So I said 3. And then notice that this is giving us an read-only list of service bus received messages. Instead of a single message, I've got a list of them. And I call await receiver.receive messages async, passing in the batch. So then, and then I can log how many messages did I get, and I can, for each message in the messages, do something. Now, it still needs a timeout because it also might be 0, but you don't have to check for null because your for each, obviously, if there's nothing in the collection, you're not gonna drop into there. So that's nice. There is a gotcha with this. There's a subtlety. When you receive your messages right here, the peak block timer starts for all of them. So let's say you pulled, I don't know if I have a diagram of this, but 10 messages, okay? And your default receive timeout is 60 seconds. And under normal circumstances, it takes you 2 seconds to process a message. You're good to go, right? Because I churned through all of them in 20 seconds. None of them timed out. Some of them got completed a little earlier in their stopwatch, but none of them timed out. Now let's say you're getting a service interruption on some downstream service. And today, for some reason, instead of 2 seconds, it's now taking 10 seconds. Well, the first 6 are probably, the first 5 will get through. The 6th one will be on the fence. And then 7, 8, 9, and 10 are all going to abandon because they timed out. And you're going to get these service bus received exceptions. Well, wherever there's no try catch here, but you're going to get exceptions thrown. So that's the only thing is like, yeah, if you pull a batch, it kind of seems like, oh, that's nice. I'll prefetch a bunch, but there is a penalty to that. And there are tools out there that default to prefetching large batches. And sometimes those tools are the dead letter factories that I was talking about. So all of that's a little lower level, but then there is this beautiful, elegant helper class called the Service Bus Processor. which wraps technically one or more service bus receivers. And in fact, you can actually F12 into that and go look, and there's a comment at the top from the Microsoft team that like a service bus processor wraps one or more service bus receivers. And so it's this construct for you that keeps you from having to plumb your own message loop. Okay, your own. So, and the way it's event driven, it's lovely. And if you just go and like do tutorials on Azure Service Bus, this is what they show you. This is what they lead with. I go at it the other way because I feel like most of us want to kind of know a little bit about the lower level details, even if then we're like, okay, cool, I'm using the convenience class, but at least I know what it's doing. So you create it, you wire up a couple of events, right? Your process message and your process error, and then you tell it to start processing. You just kick it off. And then whenever a message lands in the queue, this code runs. Just fires an event and your code runs. And it has a property called autocomplete. So what that means is when you hit this line of code, it calls message.complete async for you. You don't even have to complete it. And then if something bad happens, right? Like if you throw an exception out of here, then this will run. And then you can abandon or dead letter SCV2 in the error handler. So honestly, this is for many apps, this is just the way to go. It's really lovely. Again, in the code demo, these are all implemented and you can play with them. All right, so if we stopped right now, most of you could probably go out there and cobble together an Azure Service Bus app and it would work. But it might not be sort of bulletproof yet. So I want to just talk about a couple of failure modes, right? And things to think about so that you can make your service message-based apps fault tolerant and a little more robust. We're nearing the end. And so to have this, I'm going to just introduce another sample app here. It's not food related, don't worry. So I'm starting to get hungry. So imagine we have a weather reporting. We have all these weather stations out in the world, right? And they've got little solar panels and they're collecting information about the weather, and they are all internet, they're IoT devices, they're all internet connected, and they can report stuff. And you probably wouldn't do this, but we are allowing them to talk directly to the queue. You'd probably front it with like an Azure function or something that would then trigger the queue. But for the sake of argument, let's say we're letting them actually post messages right into the queue. And then we have a service bus processor, which handles these weather reports and receives them and saves them into a SQL database, right? Persists them. So these messages are valuable. We don't want to lose them because they don't exist anywhere else, right? They're heavy messages that are valuable and they have to get persisted. And then things downstream can slice and dice them and publish monthly reports or send out alerts or whatever this system is meant to do. So the first problem we want to talk about is poison messages. You may have heard this term. So again, I said this is implemented using that service bus processor. So here is our on message received event handler. And so let's just say that the way this worked is that the incoming message had the weather report, with the wind, temperature, dew point, whatever, in a little JSON document. So we're going to read the JSON out of the message, and we're going to deserialize it into our little weather data class. And then we'll do some stuff with it. Well, who knows what happens if the thing can't be deserialized, if it's invalid JSON? Throws, right? Yeah. So if somebody has sent you a malformed weather report, either by accident or maliciously, that is going to throw an exception. And here's the thing. I don't care how many times you try that one, it's never going to work. That's not recoverable. So that's a poison message. That's what a poison message means. And the poison is that while your system is busy handling that, it's not doing other things. So the trick is to identify them early and get rid of them. You can't stop people from sending you poison messages. You can identify them and chuck them in the dead letter queue and not retry them 10 times and do other things that aren't necessary. So that's the first thing you can do. And one way to do it, again, this is just, I'm just giving you an idea, right? Not necessarily recommending, is you could just say, try all that same code and then let's catch JSON exception. We can just use a typed exception handler and be like, well, look, if that was we know that if it threw a JSON exception, we're just going to dead letter it, log it, dead letter it, move on. Okay. So that technique supposes you've taken some time to think about what constitutes a poison message in your system, right? You understand the ways somebody could try to poison you. So you might not get 100% coverage, but you do need to spend the time to think that through. And then there's the other side, right? So a poison message will never work, but then there are things that I would call transient error conditions. And this is something where something is happening, and it's going to make it so your messages can't be processed, but it's not going to be this way forever. So, for example, let's say that after our deserialization happened, we open a SQL connection and we write the message to SQL. Just dummy code. Well, what happens if your SQL connection is down, right? Throws an exception. You might wait a minute, right? There's a timeout there. So, but SQL servers go down, right? And any dependent service, right? Like I mentioned before, that app integrated with a few different REST APIs that we had no control over, and they can be weird and stuff can happen. You can get 500 errors and 404s that you didn't expect. So, but it's not the end of the world. You just need to stand off and wait at this point. There's no point in hammering SQL Server with request after request after request if it's down, right? You got to be a little smart. So this is how I like to solve this. And so in this case, we could catch the SQL exception as catch SQL exception. And then what we're going to do is stand off and try later. And so I'm going to abandon that one. That was the canary in the coal mine, but it's going to sing. So just abandon it, put it back in the queue. And then I call this function pause the processor. So first, stop processing. No more messages, please. Right, stand off. And then drop into a little polling loop here. Again, this probably would write it differently in production, but if await test the SQL connection, then start it up and break out of my loop. Otherwise, wait a minute. So all that does is every minute it just checks to see if SQL Server came back. Once SQL Server is back, it opens the floodgates and the messages can come through. Okay, so those are two common real-world error patterns you want to think about. And again, with the poison messages, you have to think about, well, what's poison? And with these, you have to think about what are my dependencies that could cause these kinds of transient conditions that I can identify. And you do your best to cover all those. Now, that's not to say something might happen that you didn't expect, but okay, right? You tried. So that's what it takes to make these things more bulletproof. So to wrap up, on the face of it, a message-based application solves a fairly straightforward problem, and it's a fairly elegant, simple thing to implement. But with Azure Service Bus and other platforms, you have some choices. Are you going to use just basic queues, or are you going to use topics and subscriptions? What kind of messages, heavy or light? I've actually had apps that combine them, right? This queue expected a lot, and this queue expected an event. Are you going to stick with pclock and all of the flexibility and retry and magic good stuff it gives you? Or are you just going to be like, I don't want to deal with that and go with receive and delete? Are you going to implement, just use the Service Bus processor or kind of implement your own message pump? Are you going to pull one at a time, or are you going to pull batches? Are Are you going to do things that could get the messages out of order, and do you care? Like when you abandon and other things that can happen. And are you properly abandoning and retrying or deadlettering messages? Have you thought about how you're handling all of that? So there's your checklist for success, all the choices you need to make. And we'll take a little break. I think we should just take a stretch break or bathroom break. And then anybody who now really does need to leave, don't be shy, you can. And anybody who would like to stay and watch me run the code, I'll be happy to run the code, or you can just go home and download it and run it yourself. It's fairly self-explanatory. So there you go. You're on the bus. Yeah, let's just reconvene in 5 minutes. We can do Q&A and code demo. And you probably stop it. I think it's a big
you go through a report. We have a whole queue.
I think that makes sense.